sessions. We also looked at using static code analysis and understanding which classes you use need to be managed correctly. That design time work is much less effort and it gets you better quality code before you even start to run your app. Static analysis is a .NET compiler feature which you enable in your project settings, and Visual Studio hooks in and shows you the results. Code analysis can find a lot of issues and save a lot of fixing time, but you need to know that static code analysis isn't enabled by default. That's a performance thing. Running those rules adds a lot of time to the build, but when you do turn it on, the default set of rules includes the main IDisposable rule, CA2000. That identifies cases where you're using IDisposable instances and not disposing them, and that found most of the issues in the word counter code. There are some finer details on how this rule works, which you can read about in the docs here. We fixed up the CA2000 issues by wrapping local variables in using blocks, like with this example in the file archiver, which is a good use of stacked using blocks, where the scope of the objects is still clear. But the checks for rule CA2000 don't find every issue. If you create a new instance, then the rule knows that you own the object and you should be taking care of disposing it. But if you get an object as the result from a method call, the compiler can't be certain that you own the object. When you call create command on a SQL connection instance to get a command, the compiler doesn't know if SQL connection is creating a new object for you, which you should dispose, or giving you an existing object to reuse, in which case you shouldn't dispose it. So in this scenario, you don't get a CA2000 warning even though you should be disposing of the object. Static analysis catches a lot of problems, but not all of them. So you need to know how the classes you're using expect to be managed, and a lot of that just comes down to experience and understanding the domain that you're working in. We looked at a couple of extra scenarios there too. The HTTP client class implements IDisposable, but it's intended to have a long lifetime. HTTP sockets are expensive to work with, so it optimizes them for reuse. That means a bigger change than just adding a using statement. I changed the API client class to use a local member for the HTTP client and implemented IDisposable with the proper dispose pattern in that class. Then in the program class, I used the same API client instance for every service call, and I dispose of it in a finally block when all the work is done. And tasks are a special case too. Typically you work with them implicitly with await statements, or you schedule them for background work, and then you shouldn't dispose them because you're not always sure of their lifetime. But in this case, I explicitly await all of my tasks, so I know when they're done, and then I can dispose them all. This is an optimization you usually don't need, but it's good to know that tasks are disposable if you create a lot of them over a short space of time, like in this example. Those changes fixed the defects in the app and also gave us some important performance gains. In the first run of the code, the smallest files each took around 3 seconds to process, and the object allocations rose from 50,000 to 100,000 objects. The biggest file jumped to 650,000 object allocations before it started to hit errors with a maxed out SQL connection pool. The fixes, and these were all about managing disposable object lifetimes, reduced the file processing time from 3 seconds to sub-second for the smaller files, and it reduced object allocations by about 50% across the board, which had the side effect of reducing the amount of garbage collections. So this is the next best practice. Enable static analysis with rule CA2000, but don't rely on it exclusively. If you have a large code base, enabling code analysis will slow down your development pace as every build takes much longer to run. But in the majority of cases, CA2000 will find problems and help you stick to best practice number 1, disposing of resources as soon as you finish with them. But in some cases, this rule doesn't help, so you need to be aware that there's still manual work to be done, which comes with your domain knowledge. So we've got a more reliable version of the word counter app here, but the design is still pretty bad, and I have promised you a look at managing disposable objects within a more modern architecture. And we'll do that in the next demo. We'll look at a better, more solid version of the app where the work is split out between lots of smaller classes, and we use standard .NET libraries for dependency injection and data access. In this demo, we'll look at disposable objects in modern .NET apps which use dependency injection. That moves the responsibility for managing object lifetimes to the DI container. We'll have a lap around the new code base and run the new version of the app under the profiler to see how it performs. So in the same word counter solution for the source downloads, I've got this word counter.modern app, which has my more modern architecture. Inside the program class here, you can see I'm using the standard dependency injection library from Microsoft Extensions. That's a .NET Standard library, so you can use it with .NET 5, .NET Core, and .NET Framework applications. In the setup for the application, I create this service collection, and I'll use that to register all of the dependencies that my application needs to use. For my basic dependencies, I'm adding a single an instance for the application configuration, and I'm adding logging, which means each of my classes can get their own logger, which has been configured using the centralized configuration. Then I'm adding each of my own classes, so the folder watcher and the file archiver we've already seen, and some new processor classes which are going to do the actual work of processing the books when they get copied into the folder. And instead of using a custom SQL client that fires off manual SQL statements, I'm using Entity Framework here, and I'm adding my database context as a service to the dependency injection container, so objects which need to use the database can request the DB context from the dependency injection framework. The rest of the code in the program class doesn't do very much. It fetches the folder watcher object from the service provider and configures it to start watching. So the folder watcher here is the entry point for my application now. If I open this up, the folder watcher class is using dependency injection, and in the constructor it receives a book feed processor and a logger, so we don't have these console.write lines anymore. We're using the consistent logging framework throughout. The code to start watching the folder and to sleep when files are created, that's exactly the same, but now when the file gets created, the folder watcher class calls on the book feed processor to process the file. So I've broken out the logic for my application into smaller classes that each have a specific concern. The book feed processor manages reading all the contents from the file, and then it uses this book line processor, which processes each line in the book. It calls the REST API to get the word count, and it saves the data for that line in the database. This class uses dependency injection to get the objects that it needs to use. That's the database context and the API client. And the code to process a line of text is very similar from what we originally had in the program class in the older application, except that I'm using my database context here, so I can work with an object model instead of building up SQL statements. So this is all fairly standard stuff, but where it gets interesting is in the book feed processor itself. So this is the class that gets used by the folder watcher whenever a new file gets dropped. But in the dependency injection for this class, the requirements it has is the database context and the file archiver, but it doesn't receive an instance of the book line processor as a dependency. Instead, it uses this service scope factory, which it can use to resolve an instance of the book line processor on demand. So what we'll see if we go and have a look at the processing logic inside here. When a file comes in, it uses the file archiver class to copy it to the archive destination. Then it saves the basic details about the book to the database using the DB context. Then it sets up the cancellation token source, reads all the files, and kicks off all of those tasks. When each task runs, it's going to call the getWordCount method on the book line processor, but objects of that class use a DB context, and the DB context isn't meant to be shared between different threads. So when I have multiple tasks all running simultaneously, and the methods running inside those tasks use DB context, I've got to make sure that each one has its own database context instance. And that's what the service scope factory is for. So this is a built-in part of the dependency injection library. Any class can request a service scope factory, and then it can create a new scope and fetch a dependency within that scope, and then each scope has its own object graph. So for each of the tasks that run, there will be a new book line processor object that gets its own database context object. Ultimately, the book line processor uses an API client class, and we can see this will probably need a bit of work because it uses an HTTP client as a local member, but this class itself doesn't implement IDisposable. And then the file archiver class, that's got the same original code without the using statements. So the first thing we'll do is switch to release mode. We'll build this new console app, and then we'll run it through the profiler. So my profiler here is set up to launch the modern app exe in the release folder. And again, we're just doing the object allocation tracking so we can see what happens with the memory. So I'll start the application running, and I'll kick off the folder watcher. And the first thing we see is that even when the application isn't doing anything, it uses a lot more objects. So we're up to nearly 14,000 objects already, even though the application hasn't done anything yet. And then I'll do the same thing I did before. I'll start by copying the smallest file to my book location. So we can see the processing happens in the same way. The logging is slightly different because I'm not doing console.write lines. I'm using the logging framework. And if I go back and look at the object allocation here, it's significantly more than we had with our older application. So at the peak, there were 120,000 objects being allocated, and we can see there's lots of allocations and deallocations happening, which suggests the garbage collector is doing quite a lot of work. So I'll carry on and drop the second largest file. That's finished now. That took about 3 seconds to run. And again, there's been a big jump in memory usage. So we've peaked at about 280,000 objects. And even though some objects have been reclaimed here, we're still running with 230,000, even though the processing of that file has finished. And the last thing I'll do is I'll drop that full-sized file. And because we're using dependency injection and entity framework, we shouldn't expect to see any issues this time. This was the file that caused the SQL connection exhaustion when I was running with my older application before I had my disposable fixes. So it's running along nicely here. If I look, we're using an awful lot of objects. So we're up to 500,000 object allocations here. There's a lot of allocating and deallocating happening, so the garbage collector is doing a lot of work. The application certainly seems to be running a lot more slowly. And I'll pause the video here to let this run along, and we'll see what happens when it gets towards the end of the file. Okay, so that's That's all worked correctly. It took 170 seconds to complete the processing, and if I look at my diagnostics here, I can see we peaked at nearly 1 million objects, and there's been lots of deallocations happening. So it looks like there is something wrong with our application, and actually sometimes when you run this with the full-size file, you will still see SQL connection errors, where the connection pool gets maxed out because of the way we're using our database contexts. So this version of the app looks like it's a lot harder on resources than the original, but we haven't fixed up the disposable objects yet, and we'll do that in the next demo. In this demo, we'll fix up the object lifetime management in the modern application using static analysis to find disposable issues, and following that up with a look at how we're scoping object lifetimes. Some of the issues we'll see need special treatment with dependency injection, so we'll look at how that works too. Back in Visual Studio, I'm ready to start fixing up the app. So let's do what we did before, and we'll open up our project file, and we'll switch static analysis on with that analysis mode, and we'll rebuild this application. So we'll look at the error list here. We're still searching on dispose, and I see I've got 3 instances of CA2000. 2 of them are in my file archiver, so we know how this works. I'll go back to my file archiver here. I'll put my using for the input stream and a using block around the output stream, and that's going to fix those issues. I've got my cancellation token source issue here, which we knew about from the previous iteration of the application. So again, I'll put all this code within a using block. This is in the book feed processor class now, as opposed to the program class, but it's the same issue where my cancellation token source gets used to stop all my tasks if there's a problem with the processing. But that's it, I don't have any more dispose warnings, which is strange because when I did my performance run, we saw those huge peaks and troughs in the object allocation, where .NET was allocating hundreds of thousands of objects and then clearing them up periodically, which suggests that the GC was working really hard. And again, the only way to really work out what's going wrong here is to understand the domain that you're working in. And the real problem is this line of code here. So this gets me a service scope, and I can instantiate a whole object graph inside there using dependency injection, but the scope itself is a disposable instance. So every time I'm processing a line at the moment, I'm creating this whole object graph and not disposing of it. So that's stacking up all this work for the garbage collector to do. And again, CA2000 doesn't find it because the object's being created by an external method, so it can't be sure that the scope object is safe to dispose. But I know that it is, so I'll change this to be a using. And that's going to fix a lot of my object allocation peaks and also my connection pool exhaustion, which we didn't see in this run, but you may see if you run this yourself. And we know there's another fix that I can put in here because I'm managing the lifetime of my tasks. So after this try catch block, I can put a finally inside here with the same code that we've seen before, saying that we can dispose all of these tasks because we own the lifetime and we're sure that they're done with. So that's everything we need to do with the book feed processor. The main problem was around creating those service scopes. The book line processor, it takes all its dependencies via injection, and now they're all part of that scope which is being disposed, so that should all be good. For my API client, I need to think about how I'm using the HTTP client, and again, this just really comes with knowledge. You want your HTTP client to be reused, HTTP client here, with an HTTP client factory, and that requires an additional NuGet package, so I'll install the Microsoft.extensions.http package. And then I can get an instance of that factory using dependency injection. And when I make my method calls down here, instead of using a member field for the HTTP client, I'm going to use a local variable. And I'll paste this code in here to get my variable from the HTTP client factory with a helpful comment there saying that I don't need to dispose this object even though it is disposable because the factory is going to manage the lifetime for me. To make that HTTP client factory available, I need to go back to my program class, and when I'm registering my services here, I'll add one more, which is my HTTP client. And that's going to register the HTTP client factory, so my book line processor can reuse the same instance of the HTTP client, and the factory will manage the lifetime. And there's one more thing that I may want to do here, which is to do with the lifetime of my dependencies. The default for the add DB context is to use a scoped lifetime. And although I am using service scopes, my DB contexts don't span across multiple tasks, so I can switch this to being a transient object. And I'll add a comment here again saying that my DB context is going to manage my SQL connections for me. So again, DB context is a disposable object, but I don't need to dispose of it myself because my dependency injection lifetime is going to take care of that for me. So now the last class I need to look at is my folder watcher, and this has an instance field which is a file system watcher, and that class implements IDisposable. Now the way that I work with my folder watcher, I only have a single instance and it's open for the lifetime of the applications, so technically I can leave this as it is. But this is a public class and other people might use it in a different way, so really I should make this disposable too. And again, I'll implement that with the dispose pattern. And when I scroll down here, all I need to do is I can get rid of the finalizer because I don't have unmanaged code. I just have that file system watcher that I need to worry about. So if I'm disposing and the watcher is not null, then I can dispose of it and I can set it to null and get rid of this comment here. And now my modern application is going to work much more nicely. So if I rebuild this again in release mode, I'll close all these windows and I'll open my profiler and we'll get this running again for the final tests. And now I'll start the folder watcher. And again, we can see we've gone up to using kind of 14,000 objects already without doing anything. And that's just because we're using a much more complex domain to represent our application. And I'll open my folders here and we'll see how we get on with the smallest file, which is my contents file. Everything starts processing. That took 5 seconds for that run, and we peaked at 140,000 objects, and then we returned quite quickly to a baseline of about 47,000 objects, and that's staying at that level now. So if I try with a larger file, the excerpt file, that gets picked up and processed pretty quickly. That took 3 seconds this time, and again we had a peak where the application spun up to about 220,000 objects, and after the processing it hasn't returned so much, it's still using about 180,000. And now for the final test, we'll run the full-size file inside here now. And if we check how this is looking this time, we're up to about 500,000 objects. And there's obviously a garbage collection here that's taken us down from about 680,000 objects down to about 270 as the file's being processed. We can see the trend there, the object allocation is going up and up, but we hit the point where the garbage collector does its collection, and that's at about 580,000 objects. So we're not hitting those million object allocations that we had before we made the fixes to our application. So I'll pause the video here while I let this carry on processing. And we're back. The processing is completed. This time it took about 140 seconds. And if we look at our allocations here, we've still got these peaks and troughs, but they're much smaller. So we're looking at 500,000 allocations here, dipping down to 270,000, and now we've reached a baseline of about 380,000. If I run my garbage collector here, and we'll check back, there's been a big collection here, and now we're running at about 85,000, which is going to be the minimum that the application needs once it's warmed up and run through a few files. So next we'll talk about the changes we made to that modern application and the domain knowledge that you need to have when you're managing disposable objects using modern .NET libraries. Demos with a more modern design of our application, where the logic is broken down among lots of small classes. Demos, we work with a more modern design of our application, where the logic is broken down among lots of small classes which use dependency injection to get the objects that they need to work with. Mostly, that's all transparent, with Microsoft's dependency injection extensions populating objects in the constructor. But with the feed processor, we explicitly create a new service scope, so each line processor gets its own database context. You need to do that so the DB context on different threads don't end up clashing. So this snippet of code is quite advanced, but it's the sort of thing you will find if you're processing lots of work in parallel. We're calling task.run to schedule some work on a background thread, and that's going to call an asynchronous method which uses this scope factory to create a service scope. The scope has a service provider that we can use to get our book line processor, and then we can call a method on that processor object, and it will have all of its dependencies already set up by the service provider. And we needed to do that in this case because the book line processor uses a DB context class through dependency injection. DB context is not thread safe, so you can't have multiple tasks all trying to use the same DB context object, which means you need to have one DB context instance for each task, either with a lifetime that's scoped to that class or with a transient lifetime. And DB context is one of those special cases that you don't dispose. You leave it to the service provider or the service scope to work out to manage the lifetime of those objects. My line processor class also uses an API client with dependency injection, and that class has another special case, which is HTTP client. HTTP client is also disposable, but it's meant to be reused for performance reasons. And so rather than manage the lifetime of those objects yourself, you should use an HTTP client factory, which you get via dependency injection, and then you can create a client using the factory whenever you need to, and the factory decides whether to reuse an existing client or create a new one. All those services are registered in the program class, and this is using that same dependency injection library that you'll use with ASP.NET applications. There's a lot of integration with that dependency injection framework, so I can add logging and my HTTP client with a nice method overload. And I can do the same with my DB context, so I don't have to worry about how my DB context is created, because this effectively sets up a factory to create my instances with whatever lifetime I require. I'm specifying transient objects here, but if you remove that service lifetime, the default will be scoped. And all those special cases bring us to the next best practice, which is know your domain. It's not a very satisfactory piece of advice, but there are a few key classes that you'll work with all the time that you don't dispose in the normal way. Tasks, HTTP clients, DB context, all of those will have their lifetime managed in a different way, and you need to understand what works best for the way you're using those objects in your applications. So we went through and fixed up all of the issues in our modern application, and we did some performance tests with the profiler. Before fixing up all of the object lifetime issues, processing a large file took nearly 3 minutes, and during the processing, object allocation kept spiking between 1 million objects and 500,000 objects, which was giving the garbage collector a whole lot of work to do. I didn't get any exceptions when I ran the demo, but that doesn't mean they're not there, and those potential issues with exhausting sockets or database connection pools, they're still there in that version of the app. And when we fixed all those issues, we got some nice performance improvements too. We're still allocating an awful lot of objects, over 500,000 when we processed a large file, but we reduced processing time by 30 seconds, and again we did that just by implementing those IDisposable best practices. But if you compare these graphs to what we had for our badly designed original application, the performance of the modern app is actually far worse. Now those graphs don't give you the full picture because I was running under the profiler, so I ran some more tests to get a genuine comparison, and you can see that there is a cost to using these modern approaches with entity framework and dependency injection. When it's not running under the profiler, my original application can process those large files in under 15 seconds, but the modern application takes more like 25 seconds. So that's really just an aside as far as this course is concerned, but you should be aware that sacrificing some performance is usually worthwhile if you have an application that's easier to work with and easier to maintain. And with that, we've covered pretty much everything you need to know about IDisposable, except for one new feature that came in with C# 8, and that's for dealing with disposable resources when you're using asynchronous code. So by now you're really familiar with the IDisposable interface. It just has that single method void dispose, and it's part of the system namespace, and it's where you're going to clear up your managed and unmanaged resources. But this is only good if your resources can be freed up with synchronous method calls. If your resources need to be freed asynchronously, then you can't do it with the standard IDisposable interface.